Everything okay?
Okay, guys, so still we are not doing the microscopic theory, but we are slowly going to quantum and quantum, okay? So I just want to tell you that Landau made a very important phenomenological contribution. He discovered it actually not in the case of the superconductivity, but with the case of the superfluidity, which is like the charge neutral Fermi liquid. Where superconductivity is charged Fermi liquid, that's only the difference. And the Landau make the following simple argument from the observation that there is a superflow. In our case, superflow is a supercurrent. He was saying that the excitation spectrum should have a gap. And he even was able to predict what is the magnitude of this gap, okay? And how he did it, I think it's very nice. However, I think myself, I will not come to this idea. But, so Landau was considering like that I'm just writing what's written here, that I assume I have this electron gas, I call it a quantum liquid now, which is moving through your tube, like a cable, for example, superconducting cable or something, tube, does not matter, some profile, with some velocity v. This is the velocity with respect to the laboratory frame, okay? And now he is saying the following things. In the frame which is co-moving with the liquid is at rest. Liquid is in the rest, okay? And then it means that if it's in the rest, then the quasi-particle of the momentum p and omega. So he said, assume now in that frame, which is connected in the co-moving frame, which is connected with the, oh, it's somehow dying, which is connected with the liquid, basically I have this dissipation spectrum, which I have, okay? This is the dissipation spectrum in this liquid. So if I'm creating the excitation in the co-moving reference frame which has momentum p and energy omega p, then I need to calculate what is the momentum and what is the energy of this excitation in the laboratory frame. Because in the laboratory frame, that's basically when we measure, when the liquid, the walls of the laboratory frame are, so I think his argument is more to the superfluid, when he really imagined that superfluid helium was flowing over the tube. So the walls of the tube are in the rest in the laboratory frame, not in the co-moving frame. In the co-moving frame, the tubes are moving, so you need to put something more to the Hamiltonian to describe this situation that something is moving. So we said, let's do it oppositely. We go from the co-moving frame to the steady laboratory frame, okay? So we said, okay, let's calculate what would be the energy and momentum of the excitation which has momentum p and omega p in the co-moving frame. And he just said, okay, let's do it simple. What we need to do is just the, okay, Galilean transformation. If in the co-moving frame I have energy E and momentum P, that in the rest frame, which is connected with the laboratory, my energy will lose like that. Is the energy in the co-moving frame times the momentum in the co-moving frame times the velocity, which is fixed, and times the kinetic energy of that. Okay, this is the Galilean transformation. And momentum would be P prime, and it would be P plus M times V. I didn't write it like that. I just write the energy. Energy is enough, okay? So before the excitation is created, I have just the system without any excitation. So it has some energy E0 and 0 momentum. No excitation. This is just the ground state which I have. Now I am creating in the co-moving frame one quasi-particle. It's called quasi-particle. Okay, I'm creating one excitation. So now the energy in the co-moving frame is energy of the ground state plus the excitation energy, and momentum is P. So now if I'm transforming this, so the change of the energy and the change of the energy in this laboratory frame would be omega P plus P times V.
So I have a question. So
Yes.
The one that with prompt means the
Laboratory.
laboratory.
Yes.
Okay.
And this is the change of the energy, right? Change of the energy. If I transform to the laboratory frame, I always have this term, μv square, but if I'm making the change of the energy, I am just changing it. Yeah, it's subtracting out. So the change of the energy is given by that. And now he's saying, oh, let's find what is the minimum possible value of this change of the energy in the laboratory frame. So this is some positive number because this is the excitation energy. Velocity is fixed, but I still have a freedom how I will create my excitation, in which direction. What will be the momentum of that? And you clearly see that the minimum value I will get if the excitation will be created opposite to the velocity, because then the scalar product will be just minus PV. Okay? Okay. And now Landau is saying like that, system will prefer to create the excitation if this energy is smaller than zero, because then effectively you are lowering the energy in the laboratory frame. So we said, if this starts to be from some point smaller than zero, from some momentum P and from some excitation energy, then system will start to create such excitations. So he get this. Or equivalently, he do it oppositely. What is the possible minimum velocity such that I can satisfy this equation, which means that? Okay? And then you see that possible minimum velocity is the minimum value of this ratio. Okay? If it's possible to find omega p divided by p, you need to take the minimum with respect to all possible momenta. And if you get some number, then this is some critical velocity. And it means if the velocity is smaller than this critical velocity, you can never come to this situation. If your velocity is larger than this critical velocity, yes, you can create some special excitations which will lower the total energy. And this was this argument saying that if your current has the velocity which is smaller than Vc, you will never create the excitation, and it means current should flow dissipationless. Once you are making excitations which are, or the velocity of the flow is larger than that, you are start to create the excitation, and super current, super flow is gone because you are making the excitations, right? And that's exactly was his argument, that saying that the normal Fermi liquid cannot be superconducting because when your momentum is going to Fermi momentum, your excitation energy is going to zero, so this ratio is zero. So any non-zero velocity of the current automatically means dissipation. But for the superconductor, we are having some minimum energy here. But P cannot be zero, it's around the Fermi energy, so we are having this value which is non-zero. And he said, oh, if the supercurrent move, or if the condensate move with a velocity which is smaller than this Vc, and the Vc is defined here, this means we should have a superflow, we should have a gap. Right? So his logic was opposite. We know that there is such velocity, so it means there should be a gap. That was his logic, okay? Myself, I would not come with this idea. You should have this Landau geniality in some sense, but this is the logic of that. It would be written in my notes, okay, so you can read it more, but I just want to tell you that the people were guessing that excitation spectrum of the superconductor should be gapped. And that was the argument which was given on the market, okay? So, just like that. So I finish today lecturing here, and then I suggest we make the homework problem. So I will upload the file today to the Moodle, and we now solve some problems, okay? From the homework sheet, okay. Homework sheet number 6. Good. I think I can take this out. Okay, so guys, who wants to solve some problems? Who goes? Just quickly solve a few problems and you go home. Okay, Sam.
2.
What's 2? You go 2?
Yeah.
Okay. Who goes next? Let's check what was the homework problem.
So your second part for the sub problem first, he wants to prove that the combinatorial operator this will be equal, and it is obvious because for this for the I, and it can only be 1 or 0. So for the 9, it could be the same state or null or 0. So you will say or 0, and if you do twice, then it will be same. So yeah. Okay, so
Okay, to give more formal proof,
more formal proof.
would you be able? Just write n squared.
Oh, okay. Okay.
Yeah, but the logic is exactly like it.
Yeah. Oh, okay. Let me write clearer. It will be.
You can write there in the corner.
Oh, okay. It will be. It will be this or this. Okay, and if I do an I again, if I do.
No, just write it formally. Write CE twice behind. So write CE dagger CE, CE dagger CE.
Okay.
And so now write it on the red corner. Go to start there. Yeah.
Okay. Like CE dagger CE
And CE dagger CE.
yeah, and like
No, just write CE dagger, CE dagger CE, and again CE dagger CE.
okay. And CE dagger CE.
Okay.
Okay.
Now
And if this
you don't need to write anything. You just write it operator identity.
Oh.
Don't write anything.
Oh, okay.
So what can we use?
So
Guys, do you see what we can use? Yes.
okay.
So basically, you need some quantity return in the beginning of the whole sheet. So you need here. So first you need C alpha, C theta, theta of the anti-commutator is delta or beta, and there is 3 stars written in the beginning of the whole sheet. So after that, you can derive some useful formula, which is C I dagger is equal to 1 minus C I dagger I base. So you can just use this C I dagger into
Exactly.
so basically we will write it as C 1 minus C I bigger than Ci. So this becomes Ci bigger. So it's just one. So you will have Ci here. And the other term is Ci bigger, Ci bigger, Ci. So this will become 0 if you write down the second formula equation. C beta equals to 0. So which means if you take alpha and beta equals to I, so which means Ci plus Ci equals to 0, which means Ci is 0. Yeah, Ci is 0, so which means this one is 0. You can also prove from the third equation that this one is also 0, so which means this is equals to Ci, which is
Yeah.
that's all.
Yeah, we want to do it like that. Okay?
Okay.
Good.
And the second would be you will have to prove this Ni Ck dagger, and it will equal to Ci dagger, Ck dagger, and the commutator relation we will have this. Plus okay, and again, this is a commutator relation, so we
I think you may see dagger. In the second term, the commutator is C dagger.
oh yeah. And again, so for this, you will have you write it down. And you know this will equal to delta. And you write this off. Okay, and then you write these two for anti-commutator and the commutator relation, and then you will have this. You plug it in. And write it in this. And then you will find out it will be you will find this term and this term, and so you can conclude that NICJ dagger will be Ci dagger delta ij, and it will be same for delta ij Ck dagger. Yes.
Did someone has a simpler solution?
Just get rid of the anti-commutator and just write all of this in Ci and
Yeah. It's I like your solution, but I think there is a simpler way.
Okay.
Yeah, you think can you show it?
Yeah.
Or someone can show it? Please, no, it's fine. Like that, can you show it?
Yeah.
Also such that others see that there are many ways altogether. So
just write down this one, and this will become just addition. So again, just use those formulas. So the first one you can apply on this stuff. So and this will becomes delta ij. So this is just from this one angle part. You will substitute this alpha equals to I and beta equals to j. You have this one. And so you just write it as I equals ij minus I meters j meter I is minus this. And you can also use this. There's a third one. C alpha bigger, C beta bigger equals to 0. So we just use ij into this one, and you can find Ci bigger Cj equals to Cj bigger minus Ci.
Bigger.
So this one becomes minus Cj bigger Ci bigger. So this turns positive Cj bigger Ci bigger I, and this is equals to this one. So these two just is also the menu instrument. And you can just so I equals to j. So you can also write it as j.
Right? And the other one, you don't need to calculate it. You just need to, the other one can be calculated the same, like the problem number 2. Problem number 2, problem number 2. 2, 2. There is also the other things to show that NECJ is equal to different, right? There are two commutations relation to prove.
Yeah.
Either you do it in the same way, or you just take the Hermitian conjugate of the previous one. How did you do it?
You say 2, 2.
2, 2, 2, 2, 2. In problem 2, sub-problem 2, sub-problem 2.
You say sub problem 2 for what?
So there's Q,
For the same.
Q.
Oh, yeah.
But there are many ways, but I would say the simplest one is to take just the Hermitian conjugate
Yeah,
of the
just
previous equation.
Yeah.
So once you prove the equation number 1, then prove the equation number 2, you just take this Hermitian conjugate.
Yeah. I just take a Hermitian.
The Hermitian conjugate of the commutator is minus commutator of the Hermitian conjugate.
Do I have to continue for 2, 3, 2, 4, 2, 5?
Yeah, why not?
Oh, okay.
I just made something. Okay. Or I don't know, like, guys, is there a problem with the problem number 2? Which problem in the problem number 2 is complicated? Tell the Sandor and he will do it.
Yeah.
And if not, then I suggest we move to some other problem.
Yeah.
If we are communicating as always. I have feeling that like you are applying annihilation operation. Okay, then thank you. So what's the next problem we can solve? Did you try some problem? Lydia, do you have something?
Yeah.
Which one? All of them, you guys? So which one can you make for us? Any? What about problem number 5? Can you do?
Yes.
Can you also clean the table, or should I do it for you? Okay. So if you want, I can do PhD for you.
Okay, so problem number 5 is about the two-side spinless orbit model. So it's two-side, right? So it has two orbitals, and it's spinless. So every side can only have one particle. So what is the space? What is the variable state is just that either it is all state inside the orbitals, or there is like some state inside the orbitals. Particle 1, particle 1 in the first orbital, and then particle 2 in the second orbital, or it is just fully occupied there. And then if we write it in the terms of this elimination operator and whatever, okay, 0 is just 0, nothing. We create particle at the first orbital, right? So particle 1, we create particle 1 at the ground state. So we have the first orbital filled. The same, we create particle 2 at the ground state. So we have it filled. And then we create both particles at the orbital. So we have this, right? So this is like why this is called as two-side spinless model. But if we have like two-side Hubbard model means the spin. So in one orbital, each orbital we can have like the spin up or spin down.
Is it clear? So just imagine like two sides, and there can be electron here, can be electron here, can be electron here and here, or can not be. Okay.
And then we have the Hamiltonian defined as the Hamiltonian. Okay, so this Hamiltonian is without interaction. If we have interaction, there will be something like P, N1, N2, which is in the problem 6. Yeah, but we don't have any interaction here. So this is just independent particle. And then, okay, so we need to write the Hamiltonian Higgs as a matrix in this basis. Okay, so what basis? This basis, right? So we need to write Higgs in the basis of this 0, 0, 1, 1, 0, 1, 1, blah, blah, blah. So it's be like 4 by 4 matrix. So the way we do this is just simple. Right? We just take the Hamiltonian defined, and then we add on the state 0. Okay, so what is Higgs? Right? And then we add on the state 0. Annihilate 0 is 0, annihilate 0 is 0. And then we just C2 is annihilate, right? 0, 0, or whatever. So it should be the same 0. take like 0, 1, then it will be like okay, so the first particle is 0, right? So there's nothing in the first orbital. So we annihilate, yeah, then annihilate nothing will be 0. Here we annihilate the second particle, so it should become what? 0, 0, right? But we then create the first particle, so it should be 1, 0, right? And then for this, yeah, the N2 is just like defining there's particle in the second particle infinitely, so it's just the same 0, 1. There's no particle in the first orbital, so it's just like defining, okay, no particle, that's 0. So what would this result in? 0, 1 minus P 1, 0.
Epsilon 2 with the epsilon 2 because energy.
Oh yeah, epsilon 2, okay. Okay, thanks. Then the same, we do it on 1, 0, and then 1, 1. So we start in these. And the similar, and then we do it also on 1, 1. Actually, the state, you can also write the state in terms of this C, then the C whatever, but I don't like it, so we just define it as
Doesn't matter, yeah, I like it also. I'm also calculating it.
yeah. Okay. So we have now, right? We have the full definition of this Hamiltonian matrix in the 4x4 matrix. So we just write it 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 is we add a 0, 0, then a 0. So this is the Hamiltonian matrix.
Do you see? Right. So we are really using two non-interacting electrons living on two sides, and this is the Hamiltonian we described. Right?
So, okay. So if you see, this would be like a block diagonal matrix. So why can we have a structure like a block diagonal matrix? Because this corresponds to the number of particles actually. So if you analyze it, this total Hamiltonian would be like Hamiltonian when the particle is there's one particle, no particle. Hamiltonian when there is one particle, and Hamiltonian when there is two particles. And then there could be no 3 or 4 particles. Okay. So there's the maximal. So this is just block diagonal. So and then what is the problem asking? For diagonal it's fixed and block. So what is that means it's fixed and block. So for n equals to 0, for n equals to 0, the Hamiltonian is just 0. Nothing to diagonalize. Eigenvalue 0, eigenfactor over 0. And when n equals to 1 is this block, right? So when n equals to 1 would be p2 minus t minus t1. And then for n equals to 2, then the block diagonal matrix would be and then we need to diagonalize it. And the diagonalize just meaning just you find the eigenvalue and then you just do the eigenvalue this minus lambda I with the determinant equals to 0 and then you find the eigenvalue. And then what's the third one?
Eigenstate. Can you write the eigenstate? So eigenenergies we see. So first eigenenergy is 0, which makes sense if there are not any electron in the system, total energy is 0. Second eigenenergy is epsilon 1 plus epsilon 2, is if I have 2 electrons, then that's the energy. And then I have this interesting one particle sector where now there is some mixing, and the energy would be, If you write it, then it will be 1000.
Okay,
Do you have it?
yeah.
Perfect.
Okay, so yeah, just in the similar manner, so this is when n equals to 1 because when this is 0, yeah, nothing to be diagonalized for 1 by 1 matrix. So we take the Hamiltonian of this matrix minus the lambda I, take the determinant equals to 0, later we will found the eigenvalue would be the eigenvalue. U1 plus E divided by x minus E. Okay, after you find the eigenvalue, you can also find the eigenfactor. So the later the eigenfactor would be. Oh yeah, I define the eigenvalue as the energy, A plus minus, because Hamiltonian acting on the state would be the eigenvalue of the energy. Right? And then the eigenstate would be 1 over E squared. So this is the eigenvector.
In general, yes.
And then what is the next one? Or in the case E1 equals to E2, so we take now E1 equals to E2. When E1 equals to E2, then the Hamiltonian is just simply E minus T minus T E. Like this, right? It becomes like this. And then the eigenvalue would be very simple. We just take that E1 equals to E2, then this root would be would be missing. And it would become 0, and then there's only T, and then what? Yeah, and then you would get just E plus minus T, right? And then we find the eigenfactor. The eigenfactor would be so the eigenfactor would be just the plus minus state, and then there is the energy. So there's also bonding and anti-bonding state. So the bonding state would be just this one, and then the plus one, and the anti-bonding state would be just minus one.
Can you write explicitly what is plus and minus? Like this plus state, how exactly would look like?
Wait.
For the case when epsilon 1 is equal to epsilon 2.
Yeah, okay. Maybe I should talk with you. I didn't really write it explicitly. Okay, I guess for this one, the plus is just simply
Exactly.
oh yeah, why? Yeah, this is okay. So yeah, so actually the plus minus one is just exactly this.
Yes, plus and minus. In this special case, when epsilons are equal, the eigenstates in the one particle sector are just this linear combination. Alright?
For plus case, the coefficient should be minus. 0.
Yes, for plus should be, eigenenergy is opposite, right?
Yeah.
You define the plus state, you define it has
Oh.
eigenenergy epsilon minus p. Maybe it would be better to call it minus, okay, but you understand what I'm saying? Or you think is also saying it? No, it's only like, would be maybe logical if you define this state, you just give it the name minus.
Oh, define it minus.
Yeah, this defined as a minus because you are having minus here. And then the other state, if you define this as a plus, you will get that it has energy at plus,
Oh, yeah.
right? So it will be like that this plus and this plus are matching together. Yeah, but it's just the name. You can name it as you
Yeah,
want.
because I just use it as this is like the convention, right? That
Yes.
people use.
Yeah. So the state with the plus sign, the minus sign, one is called bonding state, and another call is the anti-bonding state. Right? Anti-bonding state has higher energy. But now it depends on the sign which we are having here, right? I didn't specify you whether this is positive number and this is negative number or something like that. But what you are seeing is that this one particle level, if n is equal to 1, then you are seeing there are two states. One has energy epsilon minus t plus t and another energy minus t, and we even know the wave function. Right? So the bonding state has the lower energy. The normally we call the bonding state the state which has the lowest energy, lower energy, and anti-bonding which is not having energy. Okay? And this is example of the. In chemistry, they would call that this is the basically example of the covalent bond that you are having two atoms. And they are exchanging one electron between them. Okay? And there is one electron in between them, which is like making the energy. And then you will have they will choose the bonding state because it has a lower energy. But you can still excite the molecule, and you can get to the anti-bonding state. And that's the reason why the molecules are absorbing the light, so you can get the excitation. Okay? Great. Very good. Well, I think we are at the end, right? So guys, maybe we can continue also next week with solving this sheet, okay? Because it's important to go over this problem. So I will be happy to also next time some other guys come to the blackboard because there is always the Sandala, Yuretin, Olivia, maybe Marcus will, you were also, but also guys from background would be good if you come to the blackboard and present some solutions. If you are uncomfortable with speaking in English, you can present it in Mandarin, no problem. Okay? I will just look for your formula and the other guys can come, okay? So next Wednesday, or maybe Thursday, again, maybe 1 hour, let's solve some remaining problems, okay? So I will just post the results from the exam, midterm exam, or the non-midterm exam. Maybe I will prepare one model sheet with very simple problems, with different, and I will upload my notes. Okay? Next day we start to discuss something what is called the super problem, and then maybe we start with BCS, and then later I will tell you why BCS, what was the screening, what is the ultrasonic interaction. Well, let's just start with BCS with some assumption, and let's calculate something. So we will learn the details of the information. Okay, that's it. Thank you. David, what do we need to do with this?
I think you just post the